So our next topic is one that I've to varying degrees and various focus areas had set in on presentations from several Embedded Vision Alliance member representative presenters in the past. Goxel, for example, who's towards the back of the room right now. We're going to talk about stereo camera arrangements and displacement maps for those stereo cameras. Our presenter is Tom Wilson from CogniVue. And just a bit of the abstract for this presentation. The ability to detect and determine the position of objects in 3D is important for many vision applications. Various sensor technologies can be used to provide 3D images, with stereo vision being the best established approach. Disparity map generation is a particularly important part of stereo vision processing and is very demanding in terms of processor performance, creating challenges for cost and power-constrained systems. And I'll let them tell you the rest.
Yeah, so this is a topic that I think has been talked about at least a couple of times at EVA summits. I'd like to sort of take it a bit further from where it's been left off and talk about a particular implementation approach. It's an area that we're just beginning to dig into, and I guess I wanted to come and give you a bit of a progress report. Just to give you a little bit of background about CogniVue, we're a vision technology licensing company, so we license processing core IP that's really sort of very targeted for embedded vision processing. It's what we call image cognition processing. But we also license the development tools and algorithm toolkits and application toolkits that sit on top of that. So it's just to give you a bit of a background. So first of all, let's sort of look at what we're going to be talking about as we go through this. So first of all, we'll talk about, well, what are the reasons? And we've touched on this in previous papers. I'll go through that quickly. What are the different approaches for 3D sensing? There are, of course, different kinds of 3D sensors out there. Why would you pick one versus another for a specific use case? We'll talk about that. That'll lead us to talk about stereo camera, because we'll find out that there are particular use cases of interest that really sort of lead you to use that approach. And within stereo matching, which is a problem that we're talking about, there are different kinds of algorithmic approaches that we'll talk about. And that'll lead us to dense disparity mapping, which will be the main focus of the talk. And the algorithmic approaches that you can take with dense disparity mapping. And at that point, then I'll talk about a particular implementation proposal, example, that we've actually estimated benchmark for, and compare that against benchmarks that are out there that we found in the literature. So that'll lead us to those results, and we'll talk a little bit about next steps and where we would want to go next for our next progress report when we come back. So first, let's begin with, well, why 3D sensing? And it's been touched on before. 2D computer vision has fundamental challenges with certain aspects of analyzing the scene. So things like segmentation, for example, being able to distinguish the foreground from the background is a particular problem with a 2D computer vision application. Illumination, particularly for things like face recognition, the impact of how the face is lit is huge, and this is something that really sort of goes away when you use a 3D sensor. Judging the relative position of objects with an image frame, is that a really short person up close or a really tall person far away, that kind of thing. And so 3D sensing, again, helps with that. And occlusion, hands in front of the face, various kinds of example where occlusion makes it difficult for a 2D computer vision approach. So as I said, 3D sensors do away with most of that and make it easy for us, make it easier for us to determine what's going on in that scene. Now, there are different kinds of 3D sensor technologies, and we'll look at what those different things are and what potential advantages there might be for different applications. This is something that I extracted from Calacio, I'm not sure if I'm pronouncing that correctly, 2013, who was comparing different kinds of 3D sensors. And you can see it's organized along the lines of frame rate, how sensitive it is to daylight, what the depth resolution is, what the power is. These are all critical factors, and what the working range is. Now, you'll see that with the use of stereo camera, it really sort of gives you a unique value proposition in terms of the kinds of use cases you can go after. So you can use it in daylight, you can use it for long range, and if you're in a power-sensitive kind of application, then it's quite good. Now this is power with respect to the actual 3D sensor, so it's dual image sensor, not the computational power, which is something else again. We'll talk more about that later. The challenge with stereo camera and with the disparity mapping processing that you need to do as part of outputting a 3D depth map is it's computationally intense. And we're talking about something called the correspondence problem, which is a tough kind of computer vision problem to solve. So what kind of applications would you need to use that would force you to sort of go that way and solve that problem? There's an example that I found. This was a product actually released by Subaru last year. It's called EyeSight. That's not the gesture recognition company. It's a brand name for this active safety system that they have. So it's active emergency braking, or it's automated emergency braking and cruise control, and it's completely vision-based. You can certainly see how those value propositions for stereo come into play here. First of all, power. It's not commonly known, but power actually is a real problem for these automotive cameras, and keeping power down is critical. So having something that's low power helps, but really important here, of course, it needs to operate in daylight. You can't be driving through tunnels all the time. So it needs to work in daylight, and it needs to work at very long range. So this thing works out to 80 meters. So this is a good example, but it's not just automotive where stereo cameras and these value propositions come into play, but the use of stereo cameras is becoming more prevalent and will become much more pervasive in mobile, in smartphones and tablets. That's a whole other ballgame. Now you've got a real problem to solve in terms of power and performance. Let's just quickly touch on the disparity mapping problem. Basically have a left camera and a right camera looking at the same feature. That feature is located at different points in the left image frame versus the right image frame, and basically parallax. And if the image frames are rectified, it means those features are along a common epipolar line. And the disparity offset between that same feature, if you match that feature between the image frames, that's the correspondence problem, that disparity offset is directly related to how far away the object is. So you can convert your disparity mapping to a 3D depth map. So let's look at the kinds of algorithms that are used. If you pick up any academic paper about disparity mapping, and it's a very active area of academic research, I'm sure you're aware, then the first paragraph, you're probably going to see something that talks about local versus global approaches. Global is slightly higher quality, gives you a better quality 3D depth map. Dense disparity mapping, local disparity mapping rather, works with set window sizes around pixels that you're trying to match and the intensity values in those set window sizes. However, one of the things you'll also read in those academic papers is local disparity mapping techniques are typically used for embedded applications because it's a more tractable computer vision problem. And it also happens to fit very well with parallelization. It works well with parallel architectures. So it tends to get picked. So let's focus in on local. Now, within local, there are a couple different algorithmic approaches. There's sparse, where you use some form of feature detection, whether it's FAST or SIFT or something like that, to pull out features in those two stereo frames. And then it becomes a problem of just having to match one feature or key point in the reference frame to a feature in the corresponding test frame. So you've sort of constrained the computational problem to a subset of the pixels just looking at those key points. Doesn't really perform quite as well as dense disparity mapping. If you look at how these different algorithms are rated on the Middlebury test suite, you'll find that the dense disparity mapping techniques tend to perform better. So we'll focus in on those. And those two image frames I have there are just a small example of the kind of stereo frames that you find with Middlebury where you run these tests. So what's the actual processing flow for a local dense disparity mapping approach? So first of all, you have the left frame and the right frame. You've got a pixel in the left frame, for example, with a patch around it, a block. It's also called a support window. And you're trying to match it up against the corresponding pixel along the epipolar line in the right-hand frame. And you work along a disparity range. You select a range of pixels that you're going to do your correlations against and calculate and find the match. So that's the kind of stereo matching that you're doing. There's cost calculation to do the correlation between those two pixels between frames. There's cost aggregation, which drives a decision about which disparity level you actually have the match. And that leads to, that's a disparity estimate. And some of the algorithmic approaches, not all, but quite often you'll have a disparity refinement step where you're throwing out bad pixels, noise, or whatever. So let's look at those in a little bit more detail. So cost calculation, for example, this is the correlation that you do between the pixel in the reference frame and the pixel in the test frame. And the cost calculation is for the support window. So common correlations are absolute difference or square difference, or there are different kinds of normalized correlations you can use. But let's just use absolute difference. If you've got a support window that's 7 by 7 and comparing it against a test pixel in the right-hand frame, then you have 49 separate absolute differences that you need to compute as you work your way through the support window. And depending on how many disparity levels, what your disparity range is, you have to repeat that X amount of times. So that's cost calculation. That's all the individual absolute differences in the case of a SAD approach. Cost aggregation is where you sum the correlation, you sum the cost calculations for that particular support window at that particular disparity level. It's a very expensive computational step, and I'm going to talk more about that. So for a 7 by 7 window, you're summing those 47 absolute differences for that support window, and you do that across all of the disparity levels, across the entire disparity range that you're working with. And for example, I've got here an example of 64 disparity levels that you're working with. So you can see that it begins to really sort of multiply quickly. And you do that, like I was saying, with the support windows as you track your way across a disparity range. Once you've done that, then you're able to plot the cost aggregation on a chart like this, where you're plotting the matching cost against a disparity range, and the minimum matching cost, it's kind of a winner-takes-all approach, is your disparity. That's what you pick as your disparity, and that translates directly to how far away you think it is, and that is used to create the 3D depth map. So you got the cost calculation, the cost aggregation, and then you have to sort of output a disparity based on what the minimum matching cost is. So how does that all add up in terms of actual computational loading? So this is something that I found in the paper from Fong et al. 2012. And they looked at different sorts of dense disparity, local dense disparity mapping approaches. And by far, you can see that cost aggregation, where you sum all those support windows, is the lion's share. Now, CW, the constant window, is where that support window is a constant size as you work your way through the image frame. AW is adaptive. This is an adaptive support window approach, where you vary the size of the support window depending on what the pixel intensity neighborhood and local environment is like. And that increases the computational cost. An adaptive support window is an even tougher computational problem. But certainly, if you're trying to attack the particular part of the problem that's going to give you the most gain, you really should go after cost aggregation. And that's certainly where a lot of the active research is, and a lot of the shortcuts are in terms of trying to achieve real-time performance. So let's look at some actual numbers. So let's pick an example. And this is where we actually get to sort of an implementation example that we've performed with our core to arrive at a figure, because we're just sort of beginning to do this and understand where we're starting from. And there's lots of work to do in terms of working with the algorithms and working with the hardware to change the results and improve them, but wanted to sort of give you a feeling for where we are right now with a fairly simple block matching constant window size approach. So the whole computational cost cycles, the operations are dependent on the pixels per frame. So how many pixels do you have to work your way through in this dense disparity mapping? What the size of the window is, because that tells you how many correlation cost calculations you need to do per pixel per disparity level. And also how many disparity levels that you have to work with, because that's how many times you need to repeat that for every single pixel in the reference frame. So let's assume that it's a megapixel frame, 7 by 7 window. It sounds like an odd size, but it's a size you see fairly often, and often they're sort of odd size frames. And we'll go for 64 disparity levels. So this is actually quite heavy. Just brute force, if you add up all the operations that are necessary to achieve 30 frames per second, you're at around 800 billion operations per second to achieve that. So it's really heavy-duty computational complexity. So what we found is just taking a simple block matching approach that we've been talking about, a version of our core called the Apex 1284 achieves about 30 frames per second at about 2,700. Now those MDEs are millions of disparity estimates per second with those above assumptions. We're doing it at quite low power. So with some algorithmic optimization, a factor of 3 or 4, which is not uncommon, getting down to the range of 30 to 40 milliwatt for a megapixel frame for disparity mapping, for dense local disparity mapping. That was very encouraging. And then what we did, well, that sounded good, but we weren't sure. Let's compare that against what you see in the literature for different kinds of architectures. Let's look at high-power desktop GPUs, for example. So this chart shows some results from Kawachuk et al. 2012, and he was looking at different kinds of local dense disparity mapping approaches, adaptive support window, cross, where you're just looking at the vertical and horizontal pixels in a support window, various kinds of approaches to optimize and cut down the cost aggregation computational cost for that particular GPU. We're looking GPUs with cores in the range of 100 and some to 500 and some cores, and 200 watt, 150 watt. What we found is that we were actually able to achieve with 128 cores better performance in terms of million disparity estimates per second and much better frames per second at much lower power, at less than 200 milliwatt versus 200 watt. So that was nice, but now we can talk a little bit more about how we achieve that. And how we achieve that is because we've really architected the data path and memory architecture to maximally pipeline the algorithmic process and make maximal use of intermediate results, which is really key. So let's look at that in a little more detail. So there's a lot in this, this image. I don't have a pointer, but I'm just going to walk, if you can hear me, thanks. Down here is what we call the apex, and along the top is ACP, array control processors. Under that are CUs. If you can see that, they're computational units, and those computational units, there are 64 of them in this architectural example. Each one of those computational units has got 4 kbyte of memory attached to it. And the trick that we applied here is we also have some sophisticated DMAs that move large slices of image frame data into the CMEM in multiple copies, so we can use multiple large slices of image frames. The trick here is the large slice, and this is 512 pixels wide and 64 scan lines deep. It's oriented when it goes into CMEM such that the scan lines run down the CMEM. So you've got a left slice and a right slice with the epipolar line oriented along the CMEM. So now a pixel in the left image, for example, the reference pixel, can be compared by one CU against all of the pixels in the disparity range along the epipolar line. And that's very efficient computationally. There's no moving data around. The data's there. The whole thing about this is to move data as little as possible. So for a support window 7 by 7 again, you're looking at a pixel in the left image and a range of 7 pixels down in the right-hand image in the same memory. So you can go through your absolute differences very quickly in very few clock cycles. Meanwhile, you've got those 7 scan lines for the 7 by 7 window arranged next to each other, and you can shuffle results and make maximal use of intermediate data. What we can also do at the same time is, as we're working through the slice, be generating those minimum matching cost calculations in a separate part of CMEM and build a 3D depth map as we go along. So again, there's no data moving out of the core and back in again from external memory. It's all kept right there. The slice is processed locally, and we output at the end of that slice a 3D depth map of that slice, And while that's getting output, we have another large left and right image frame slice ready to go. So it's all about maximum reuse of intermediate data and moving data around as little as possible. And that's really how we achieve the kind of results. Now, this is a very simple, no frills, block matching, local dense disparity mapping approach, but there are a number of different algorithmic tricks left to play. So for example, just looking at various kinds of examples in the literature, Chowdhury et al. And Bunan in 2009 talked about an average disparity approach. They used intensity threshold when they were comparing the reference pixel against a matching pixel, and could discard pixels that fell outside of a particular intensity range. So that allowed them to greatly reduce the computational load in terms of cost calculation, because it reduced the number of support windows, and cost aggregation, which is really important. So they improved the real-time performance by about a factor of 2, and actually improved their 3D depth map quality as tested against the Middlebury test suite. So that's something to try right there. Also, there's been work recently on the use of integral image for disparity mapping as well. The computational cost for the cost aggregation, particularly in the cost calculation, is directly linked to the size of the support window. The bigger the support window, the more absolute differences you have to do, and you know, there's more sum calculations you have to make. There's more adds. You can reduce that. Once you pay the cost of doing a summed area table, you can, with an integral image, read off the area of any arbitrary size block in an image frame with constant computational cost. So there's a great advantage to integral image. So let's look at that just a little bit more. With a constant window size for dense disparity mapping, it's very difficult to guess what the right window size should be, because the intensity neighborhood can change through the image frame. So that's why adaptive window works so well. Problem with adaptive window is changing the block size, you change the computational loading. Integral image allows you to change your block size, your support window size, with no extra computational cost. It stays constant. So this is something that we're going to explore next. It's something that we're going to apply, and so stay tuned. We're going to come back and talk to you more about the impact of integral image with the architecture that we've been talking about for dense local disparity mapping. So just to sum up, 3D sensing solves a lot of problems that you see with 2D computer vision. There are different sorts of 3D sensor approaches, and there's a real important class of applications where it's very important to have stereo camera. It's shown, at least in this initial work, that the Apex architecture that we have provides significant advantages in terms of this computational problem, and it certainly has encouraged us to go and explore further the optimizations and drive megapixel dense disparity mapping down to the range of 10 milliwatt. Thanks.